Welcome. In today's video, we are going to derive the moment generating function for the gamma distribution. To begin with, recall that if a random variable has a gamma distribution with, say, parameters alpha and beta, then the probability density function, or the PDF of x, is given by the following. F subscript x of x is equal to beta to the alpha over gamma of alpha x to the alpha minus 1 e to the negative beta x, noting that this is true for x greater than or equal to 0. Note that the gamma function here is defined for all a or for all alpha greater than 0 by the, or all alpha greater than 1, by the following expression. 0 to infinity of e to the negative x, x to the alpha minus 1 dx. Or alternatively, it's equal to simply alpha minus 1 factorial, where alpha is an element, I should say, of the natural numbers. So, to derive the moment generating function, we're going to use the definition. So mx of t is by definition e to the tx, the expected value of e to the tx. Now, the gamma distribution is a continuous distribution, which means we're going to use the continuous form of mathematical expectation. So we have x, the integral of x on the support of x, of etx multiplied by the probability density function of x, all integrated with respect to x. Now, in this particular instance, we know that x is or greater than 0, or as the support of x. So in this case, our terminals can simply become 0 to infinity. We've still got our e to the tx here, and now we're going to multiply by that probability density function, which is b to the alpha on gamma of alpha, and I'll bring it up just here, x to the alpha minus 1, e to the negative bx dx. So we have an expression here that we can now try to integrate. Now the first thing I notice here in this integral is that we can actually group the e to the tx and the e to the negative bx together. So in doing that, what we have is 0 to infinity of beta to the alpha on gamma alpha, x to the alpha minus 1, x to the alpha minus 1, not 11, and then e. Now in this particular instance, I'm going to try and keep this negative coefficient there. So I'm going to say that's negative b minus tx, all in brackets. And I've sort of done that in a smart way, because what I'm going to do now is I'm going to, in fact, rewrite this expression a little bit differently. And I'm going to write that as 0 to infinity of beta to the alpha, gamma of alpha, x to the a minus 1, e, and I'm just going to basically relabel this b, or negative b minus t, as negative sx dx, where we're going to define s is equal to just b minus t. And we're also going to assume here that this s is greater than 0. So the reason I've assumed that s is greater than 0 here is because we're integrating from 0 to infinity, which will, if we do this integral and this s component actually ends up being negative, which means negative s is positive, this exponential will blow up, and therefore the integral will blow up and not be defined. So I'm going to add this sort of restriction on our parameters. So keeping all that in mind, we're going to copy that to the next page, and we're going to continue with this expression here. And again, we've got to get mx of t is equal to that, and recall that s is equal to b minus t, and that's greater than 0. So on this next page, what we need to note here is that we have this expression here that oddly looks familiar. In fact, it looks so familiar that if we go back to the previous page and we look at this expression here, what I'm going to call this is I'm going to call this the kernel of the distribution function. So you can think of a distribution function, probability density function, sorry, as a multiplication of two components. A kernel of the distribution, which is actually dependent on the variable itself. Here we've got x and x. And then we've got a multiplicative factor out the front as well, which is independent of x. So what you can notice here, what we would call this here, if we were to ignore just the factor out the front, we could recognize this to be the kernel of the gamma distribution on its own. And if we have a look here, that looks oddly familiar. This looks like the kernel of a gamma distribution, simply with a new parameter, s. So what I'm going to sort of cheekily do here is I'm going to first take out this out the front of the integral. So I'm just going to put that out the front of the integral, or just the beta to the alpha for a second at the front of the integral. 0 to infinity. I'm going to keep our gamma of alpha there for a second on the bottom. I'm going to keep the alpha minus 1, and I'm going to keep the sx here as well. But I'm going to do something a little bit tricky. What I'm going to do is I notice again that this is the kernel, and if I recall, if this is the kernel, what would I have to put here? Whoops. What would I have to put in this position on the numerator so that this looks like the probability density function for this specific kernel? And the answer is, instead of beta to the alpha, which we had before, we actually need an s to the alpha here. And similarly, what I'm going to do is I'm going to divide by s to the alpha on the other side, such that if technically I were to cancel those components, then technically I could, although I'm not going to. That's not my objective here. But effectively, I would have the same, I still have the same expression as I have up here. So now that we've done this, what we can do, and by the way, we can do this with the s to the alpha again, because s is not dependent on the integral, or what we're integrating with respect to. So after we've done this, we can rewrite this as beta to the alpha. I'm going to replace our version of s here, which is just beta minus t to the alpha, noting that this expression now becomes something very interesting. This expression is a probability density function, and we're integrating the probability density function over the entire support of x. So, what do we know about properties of probability density functions when they're integrated with respect to their entire support? They simply just become 1 by definition of what a probability density function is. And this is the key to to computing the moment generating function for a gamma distribution. It is to cleverly insert a new parameter into our integral, divide by that same parameter, and then come up with our expression for the moment generating function. Now I'm going to do a little bit of simplification here, in that I'm going to first put beta on beta minus t to the power of alpha by combining the numerator. I'm now going to put the reciprocal function here, so I'm going to put b minus t on beta on the other way around and to the power of negative alpha. That way, when I evaluate this expression, it simply becomes 1 minus t on beta to the power of negative alpha. And recall our property that above here, that beta minus t is greater than 0, or alternatively, we can write t is less than beta as our condition, or for where the moment generating function actually exists before the integral explodes to infinity or diverges to infinity. So, all good and well. So let's have a look at how we're going to now derive the moments of the distribution. And I've actually purposefully put it in this form so that we can more easily differentiate with respect to t. So, without further ado, to derive the moments, we first need to find the derivatives of the moment generating function. So the first point of reference is to take the first moment, or the first derivative, which is the differential of 1 minus t on b to the negative alpha. Now, this is quite simply a power inside. So we can take the derivative of it's a linear function of t to the power of a number. So we can simply take the derivative of the inner function, d on dt, of 1 minus t on b, and then multiply it by, bring down the power, negative alpha, multiplied by 1 minus t on b to the power of negative alpha minus 1 as our expression. And if we put that all together, we have negative t, the derivative of negative t on, or 1 minus t on beta, simply becomes negative 1 on beta, and then we still multiply by negative alpha, 1 minus t on beta, negative alpha minus 1, which then simplifies to alpha on beta, 1 minus t on beta to the negative alpha minus 1. And there's our first expression for the first derivative. We now go on to the second derivative, but before we do, let's just copy this down so we have a record of it in the next page. Paste that item. So again, we've got our first derivative with respect to t. We take our second derivative with respect to t, and that's the derivative of the moment generating function. By definition, we can think of that as mx of t prime, which we know to be d on dt of alpha on beta, 1 minus t on beta to the negative alpha minus 1. Now, again, with our expression here, this is just a constant with respect to t at the front, so we can just leave that out the front, multiplied by, and again, we need to take the derivative of the inner function, so we take the d on dt of 1 minus t on beta times here we have a power function with respect to t. So we take down the power. So we've got minus alpha minus 1 multiplied by the original function 1 minus t on beta, and now to the negative alpha minus 2, 1 off the power. After some simplification, we get is equal to alpha on beta multiplied by, again, the derivative of 1 minus t over b just becomes negative 1 over b. Then this expression here, our negative alpha minus 1, we can simply write as times negative alpha plus 1. In other words, take the negative 1 out as a constant factor. And then here we still have our original expression for 1 minus t on beta to the negative alpha minus 2. Putting this all together, we can now loop together everything here, noting that the two negatives cancel with one another. The a and the alpha plus 1 can be combined on the numerator, and the betas can be down here, can both be combined on the denominator. So we've got a beta squared down here. And again, we still have our expression for t on beta negative alpha minus 2. So keep that all in mind. We can now find the moments of the distribution and recall that by definition the first moment of the distribution is equal to the moment generating function, or the derivative of the moment generating function evaluated at 0. Now again, recall that our expression for the derivative was alpha on beta 1 minus t on beta to the negative alpha minus 1. Evaluate that at t equals 0. We substitute in our expression here. We've got alpha on beta 1 minus 0 on beta to the negative alpha minus 1. This term inside the numerator simplifies down to, this term inside the bracket simplifies down to 1. So we've got alpha on beta times 1 to the power of negative alpha minus 1. And we know that 1 to the power of anything is simply 1. So what we're left with is simply alpha on beta. And by definition, we know already from our knowledge that that does happen to be the first moment of the distribution. Our next course of action is to find the second moment of the distribution. So our second moment of the distribution is defined as the second derivative of the moment generating function evaluated at 0. And here I have the expression that we derived before, alpha on alpha plus 1 beta squared. And remember, it was 1 minus t on b to the power of negative alpha minus 2. And again, we need to evaluate that at t is equal to 0. This becomes alpha on alpha plus 1 on beta squared times 1 minus 0 over beta to the negative alpha minus 2. And similarly as before, this expression here or the inside the brackets will collapse to 1, and then 1 to the power of anything will become 1. So this whole expression here becomes 1, which means overall we're left with just alpha on alpha plus 1 over beta squared. Finally, we can use all of this information to derive the variance of x, and we know that the variance by definition is given as the expected value of x squared minus the expected value of x all squared. Substituting in our two formulas, the first one we have alpha plus 1 times alpha over beta squared minus alpha on beta all squared easiest way to derive this now is to expand the brackets here. So we've got alpha squared plus alpha when we expand the numerator here. We've still got our minus beta squared, beta squared at the bottom. Then we've got our alpha squared at the top, our beta squared at the top, and quite nicely you'll notice that the numerators are identical, which means we can actually just subtract, the denominators are the same, which means we can just subtract the numerators from one another. And so this alpha squared cancels with this alpha squared, and what we're left with is alpha over beta squared.